suppose this is a very honest representation of what a PhD and a master's entails. It is 20 to 7 on a Tuesday evening, and I'm sat in my window reading my master's dissertation to try and tell people about it tomorrow because I have apparently forgotten everything about time crystals in 5 months, 4 months. I don't actually know. I can't count. When did I? 3 months. That was embarrassing. I really can't count. This is what university's like. It's being an adult. It's very fun. I've spent all day doing loosely stuff that I needed to be done, and I still haven't done this. And I've got to go on a run, so I'm going to be running in the dark. Fun, isn't it? Well, hello YouTube. Completely different style of video now than any of the stuff I uploaded, which has just been cyclocross, to be honest with you. Basically, I've been toying with the idea of doing this. I've decided I'm going to. I'm practically just going to vlog my entire journey of doing my PhD, which I, technically speaking, started yesterday. As a bit of a personal journal, it's something I really think I'll enjoy doing. And I think it'd be really nice to look back on in 4 years, 4 years when I graduate, and just sort of look back on sort of struggles, what went well, what didn't go well, a bit of like a personal journey. And I also think it will be hopefully quite nice for some other people if people start to follow along, because I know when I was in sixth form, I remember watching a lot of Simon Clarke. His vlogs when he was doing his PhD in atmospheric physics, and I just found it so interesting to sort of get an honest representation of what it's like to do a PhD or high level academics, and sort of do that alongside everything else I'm doing. So obviously nothing's changing with my sport. I'm still hopefully going to be uploading a fair bit of cycling content. But I think it's just one of those. I think it'd be really nice to look back on it. I hope some people enjoy it. My PhD is technically in chemical engineering. So I am looking into quantum photonics for quantum sensing. So we're basically trying to use quantum photonics, which is a study of quantum mechanical properties of light, to develop some new technologies to help study blood and different things within blood, diabetes, lactate, etc., and find some really cool new methods of doing this. But the crux of this video, what I'm going to very loosely explain, is going to actually be my master's degree, or my master's dissertation, I suppose. So my master's was in theoretical physics. I did my master's. I'm doing my PhD at the University of Leeds, which is where I sort of live and do all my work. My master's was in, as I say, in theoretical physics. It was in the field of quantum many-body physics, which specifically I was looking into something called time crystals, which I'm going to explain in a little bit. But it was something I really enjoyed, and I was sort of on the fence with, obviously, overall stuff happened over lockdown and all that. And I wasn't sure if I really wanted to continue with academia. I was sort of tempted to just get a job, do something as I graduated. But doing my master's actually sort of, I actually really like just having a problem and just working on it for 4 years. Well, I don't know if I like it for 4 years, but I enjoyed it for a year with my master's. It's very rewarding. These videos, I have no idea what's going to be in any of them. I don't even know. I'm hoping they'll be weekly. They might not be, but I'm just hoping they're quite enjoyable. And hopefully it'll be nice for people to watch, for me to look back on as well. And if anyone's interested, I am actually sat in my window for all these videos and all the vlogging, just because the lighting's better. I did record this sat at my table, but the lighting just wasn't very good, to be honest with you. And I thought it was just a bit better here. So, um, which if it make I was already sat in the window to read my disc, so come see, come saw. But yeah, hope you all enjoy. I've just started recording and realised our errors behind me. Um, yeah, so the very I'll try and give an overview basically of what my masters was about. So time crystals, I suppose, is the place to start. When we think of spatial coordinates, they exist as in we can describe, an object has this position in space, assuming you three-dimensional Cartesian coordinates, what we used to are x, y, and z. Um, you would say that there's a spatial symmetry because, in theory, if you were to do an experiment here or somewhere else, you move maybe a meter to your left, it shouldn't affect it, assuming all other conditions are the same. When you have something like a crystal, so a solid lattice, I'll try and throw a picture up on the screen if anyone's never seen this before, there's a set distance between each atom. Obviously, we know atoms vibrate at different temperatures and kinetic energies, but for the sake of argument, they have a fixed location. So if you move a certain distance in the space, there'll be another atom, which means that you can have a guarantee result. This is called spontaneous symmetry breaking because you are breaking down the symmetry of space. So the idea of a time crystal is basically the exact same but for time. So there is this existence of a continuous, or I don't want to call it continuous, but a symmetry of time where if you do an experiment today, you do an experiment tomorrow, you don't know, you shouldn't, you will get the same results, sorry. But when we look at time symmetry, and with time crystals specifically, because of how they work with their oscillatory behavior, at certain fixed periods of time, some delta t, that you'll receive a result. That is spontaneously breaking time symmetry, which is sort of one of the key attributes of a time crystal. It's very, very strange. That's why it becomes such a popular idea, because that's quite insane that happens. There's two other pre-factors for something to be called a time crystal. One, which really interestingly, I found one paper that calls it crypto equilibrium, which was in Nature, I believe, which is a big scientific journal, but not actually that much information or not naming on it. It's basically the idea because they can exist in the equivalent of their ground state for a quantum mechanical system, which just means they're at their lowest energy. When they oscillate, they don't produce entropy. It's quite odd. Entropy is the amount of disorder in the universe. There's many bits of research gone into entropy. I'm not going to deep it because it's not my field of physics. I don't like thermodynamics. Well, I do like thermodynamics, but it's a lot. But yeah, that's sort of the two main ones within them. Apologies. So it's the idea that the amount of time shouldn't matter within a time crystal. As long as it's a fixed period, it doesn't matter. It's analogous to a crystal where the fixed atoms are. There's no, in theory, an atom can be infinitely big. It can't because of energy expenditure, but there's, the distance between the atoms doesn't matter. As long as they're consistent. The same with time, long range order. It's the third corollary, I believe, is the technical term. It's all quite interesting though. But yeah, I basically took these time crystals and I applied a potential term. So I was using a Floquet model already, and I applied a term which basically enacted having two of these crystals within proximity to one another, and it done this all computationally. So I ran some simulations and I looked at what happened. So when you ran these simulations, what I found was practically having a term that makes the time crystals interact didn't actually do a lot, which I didn't actually expect. I sort of assumed having time crystals close to each other would probably impact the oscillatory behavior because they bounce, they go between spins. And I sort of figured having them, especially if they're out of sync, if you imagine sort of something spinning saying at like a top state of a spin and saying at a bottom of state, I assumed if they were close to each other, they would cancel out almost, like interference with, you think like in the ocean, if you have two waves, a big wave and over a trough, a peak and a trough, they cancel out, you get nothing. But that wasn't really what we found. We found that for most perturbations and most inputs, nothing really changed through a time crystal. But there was a select few when we used Hermitian matrices with only real entries that they didn't break down, or they completely broke down, which was really strange. My conclusion from my dissertation basically was I wish I had more time to look into this because it's really odd. It stumped me and the PhD student I was working with, which in all fairness, this wasn't his field, so I'm not surprised it stumped him. But it's really interesting. I really enjoyed the masters. If people are sort of a pretty whistle-stop tour of it, but if anyone's actually found this interesting, I'm more than happy to go through this in a bit more depth. I'll throw some little links in the description as well for a few of the bits I spoke about, and like the 2 letters Frank Wilczek wrote initially on time crystalline behaviour. But yeah, basically, as I say, I looked into what happens when they're close together computationally, and that was the crux of my masters. I spent a year, well, 9 months, I suppose, working on this, modeled it all in Python, and that's that. Yeah, that's my masters. So I don't know what else is going to be in this video, so it feels odd to do an outro, but whatever the next clip is, enjoy. Yeah, so end of first week PhD, I've just done my lab inductions, so I'm now allowed to do stuff in a lab, which is very odd considering I'm a theorist, but all good fun. I hope everyone's enjoyed the first video and stay around, I suppose, as I say, hopefully weekly-ish vlogs about what I get up to. So thank you for watching, and see you next week.